Welcome to example 5. What we have here is a battery, 100-volt battery, that's connected to two large parallel horizontal plates. So this upper plate is connected to the negative terminal, hence it's negatively charged. The lower plate here is connected to the positive terminal, so it's positively charged. And we have an electric field that is established going upwards from positive to negative, because electric field lines are always leaving the positive and going towards a negative, because they're defined for positive test charges. This field is stated to be nearly uniform and has this magnitude of 1 times 10 to the power of 4 newtons per coulomb. The reason why we say uniform, you'll see all these field lines are all parallel and equally spaced, which means they have the same magnitude. Suppose that the lower plate has a positive test charge, so the electric field points vertically upwards. What we're looking for is if there was an electron here that was released, we would like to know if it was released from rest, what would be the speed that it would strike the bottom plate at. So what kind of information do we need to know? Let's start off by writing some given information and then think about what we need to know. We have the mass of the electron must be given because it's stated here, and that's true. We do need the mass of electron, 9.11 times 10 to the power negative 31 kilograms. We have the strength of the electric field, which is 1 times 10 to the power of 4 newtons per coulomb. We have the plates are 1 centimeter apart. Let's just call that delta x is 1 centimeter, okay, which is 0.01 meters. We have the voltage, but actually we really don't need that. We'll put that down. We also need to know the charge of an electron. That's 1.6 times 10 to the power negative 19 coulombs. Okay, so let's go about solving this and thinking our way through it. If we know the electric field and we know the charge of an electron, we should be able to determine the force, because we learned earlier that the electric field is defined as the force per unit charge. So if we cross multiply, we'll find that the electric force, we'll call that Fe, is Q times E, the strength of the electric field. So let's go ahead and calculate that. Q is 1.6 times 10 to the power negative 19 coulombs, and E is 1.0 times 10 to the power 4 newtons per coulomb. So that works out to be 1.6 times 10 to the power negative 15 newtons. And you might be thinking, well, this electron's falling vertically, so shouldn't it have gravity? So yeah, sure, we'll go ahead and calculate the force of gravity. Fg equals m times g, which is 9.11 times 10 to the power negative 31 kilograms, times g, which is 9.8 meters per second squared. And that gives us 8.93 times 10 to the power negative 30 newtons. And you can see that the force of gravity in this case is quite small compared to the electric force. So we can, I would say, neglect this. It's negligible. Okay, so really our force that's acting on the electron is really just 1.6 times 10 to the power negative 15 newtons. We're not going to add this in there because it's not going to make any difference. So now that we know the force that acts on the electron as it's pushed downwards by this electrostatic force, we want to find the speed that it reaches the bottom. Now to find the speed, it must have been accelerating to get there. So let's find the acceleration. If you recall, F equals ma, so the acceleration is equal to the force divided by the mass. Again, that's the mass of an electron. So the force is 1.6 times 10 to the power negative 15 newtons, divided by the mass of an electron, which is 9.11 times 10 to the power negative 31 kilograms. And that gives us 1.76 times 10 to the power 15 meters per second squared. So now that we know the acceleration, we should be able to determine the velocity. And to determine the velocity, what we'll use is we know that the velocity of the electron initially is 0 meters per second, and we know the horizontal distance that it went downwards was 1 centimeter. So and we now know the acceleration. So let's go ahead and use v squared equals v0 squared plus 2a delta x. The initial velocity is 0, so we can cancel that out. So v would be equal to the root of 2 times that acceleration, 1.76 times 10 to the power 15 meters per second squared times the horizontal distance it moved, which is 0.01 meters, and the square root of all that. And that will give us 5.93 times 10 to the power of 6 meters per second. And so that's answer for A. B is asking how long it takes it to reach from the top to the bottom. So that's just another kind of kinematics problem. There's a lot of ways you can do it. Now that you know the final velocity and the initial velocity and the acceleration, you could just use v equals v0 plus at. Again, the initial velocity is 0. So the time would be equal to that velocity we just figured out, 5.93 times 10 to the power 6 meters per second divided by the acceleration we determined earlier, 1.76 times 10 to the power 15 meters per second squared, and that will give us 3.37 times 10 to the power of -9 seconds. And that's it for this example.